So today we're going to talk about normal distributions and z-scores. First, I have a little activity here, which I've actually, for time, already done for you, and because we've done it before in this class. So I have a frequency chart there with the sum of two dice, and I created not a histogram, but a bar graph. And it's a bar graph because the sum of two dice is a discrete variable, and we would represent a discrete variable with a bar graph. What I did next here is I put a dot on all the midpoints of each bar, and I drew a curve that passed through them. And if we look at this curve, it will hopefully jog your memory back to when we talked about types of distributions. This belly curve was what we actually called a normal distribution. And I'm just going to move to a nicer graph here for a second. So a normal distribution, it's distributed around a central value, and it's symmetrical. So that means that in the middle here, where I have drawn this green dashed line, if you folded it, it would be the same on both sides. Okay, it's perfectly symmetrical. It has that bell-like shape. And an interesting thing about it is that the mean, median, mode of a normal distribution are all the same. Okay, so if you think about it, it's equal amount of data on both sides and the highest points in the middle. So that's going to be the average. It's directly in the middle, so it's definitely the median. And it's the highest point because it's the tallest bar, so it's also our mode. Okay. And you'll notice that this graph is a little different than the last graph I showed you because instead of frequency, they put theoretical probability, but those two graphs actually end up being exactly the same other than just the numbers on the y-axis. So why would we want to draw that curve? We drew it because the area under a curve is the probability of an event occurring when we have a probability distribution. So, for example, if we wanted to find the probability of rolling less than 5 on the two dice, we actually now have two ways to do it. We can do it using adding up all the compound events. So rolling less than 5, we could add the probability of rolling a 2, plus the probability of rolling a 3, plus the probability of rolling a 4, which in this case would actually be easier. Or we could go to our graph and this curve that we've drawn, and we could find the area that was less than 5. So in other words, this area here between 2 and 4. And that would actually approximately, pretty closely, give us the same value. And you'll see that often we do want to find the probability that a variable falls within a particular range of values. And the way we're going to do that is we're going to find the area under the curve in that same range of particular values. And why we're doing that will become a little more apparent once we use some examples where we couldn't have found it some other way. We couldn't have easily found it some other way. So first we're going to talk a little bit more about properties of a normal distribution. So the first thing is recall that mu means the population mean, and this whistle, i.e. lowercase sigma, is the population standard deviation. So down here I've drawn a little normal bell-shaped curve, and in the middle is going to be my mean. Remember, it's also my mode because it's the highest point, and it's also the median because 50% of the data lies on one side and 50% of the data lies on the other side. Now here it does mention that if we had a smaller value of sigma, the data is going to be clustered and we'll have a narrow bell. And if we have a large value of sigma, the data is going to be more dispersed and it's going to be a wider bell. So what that really means is that if the standard deviation is small, so in other words, if that sigma is small, it means we have clustered data, right? Because if the standard deviation is small, it means it's not spread out. So you're going to get a much narrower, skinnier bell. If you have a large sigma, that means that the data has a lot of spread in it, and it's going to be really stretched out, and so it's going to be a very wide, flat bell. So based on the shape of the bell, you can get a reasonable idea as to whether you had a big sigma value or a little sigma value. But the most important thing actually about normal distributions comes here at the bottom. So it tells us that for any normal distribution with a variable x, approximately 68% of the data values lie within the range of mu minus sigma and mu plus sigma. So what that actually means is that if we took our mean and if we subtracted a standard deviation, we did mu minus sigma, and then if we took our mean and we added a standard deviation, so mu plus sigma, the data that lied in this curve, or under this curve here, so all of this would be 68% of the data. So you have a 68% chance of finding your data point in between the plus 1 standard deviation and minus 1 standard deviation. Now, if instead of doing plus and minus 1 standard deviation, we did plus or minus 2 standard deviations, so in other words, sigma minus 2, mu minus 2 sigma, I should say, and then mu plus 2 sigma, the data that falls in between those two values is actually going to be 95% of the data. So most of our data falls within 2 standard deviations. And if we went to 3 standard deviations away, so in other words, we subtracted 3 standard deviations from the mean, and we added 3 standard deviations to the mean, in between those 2 green lines there is 99% of the data. So what that means is it means that in these little tails off to the side, actually only falls 1% of the data combined. So this one tail here only contains 0.5%, and the other tail would only contain 0.5% of the data. Okay. So most of your data is going to be within 3 standard deviations. It'll be very rare that you get data outside of there. Okay. And when I say that 68% is between sigma minus, or mu minus sigma and mu plus sigma, since it's symmetrical, that actually means that 34% is in each. So this one side is 34%, and this other side is 34% to make up the full 68. So now, just based on how many standard deviations we are away from the mean, we can actually tell how much data is there. And we're going to use that to solve our next example. So here we have Giselle. She is 68 centimeters tall. In her high school, boys' heights are normally distributed with a mean of 174 centimeters and a standard deviation of 6 centimeters. What is the probability that the first boy Giselle meets at school tomorrow will be taller than she is? So we are trying to find out what is the probability that X, which is the first boy she meets, is greater than 168 centimeters tall. So that's what we want to figure out. Now, what's important to recognize here is they told us that the heights were normally distributed. So we are going to draw here a normal distribution. And we know that in the middle is going to be the average, which is 174. And we also know that the standard deviation is 6 centimeters. So, to solve this question, Giselle is 168 centimeters tall, so she's going to be just on this side of it. And we're trying to find the probability that we are on the right side of that green line. So all of this. Now, if we find the distance between the mean, which is 174, and her height, which is 168, that distance is 6 centimeters, which just so happens to be 1 standard deviation. So Giselle is actually 1 standard deviation away from the mean. And what's great about that is if you look back at our last graph, the amount of data that was between the mean and 1 standard deviation was 34%. So we know that in this green area here, there is 34% of the data. And now we just need to worry about this other half. And what's important about that is that it is in fact exactly half. And so if it's half, that means it's going to be 50%. So in total, the probability of being greater than this green line, greater than 168 centimeters, is 84%. So she has an 84% chance of the first boy she meets at school being taller than she is. And I'm going to continue this on the next video.